I'm going to start with a little news headline, okay? And this kind of corroborates my theory. We're going to talk about belief now, okay? So it's not really about science. It's not really about physics. It's got to be about religion. I'm going to show you that I have proof, evidence, okay, for my theory, my rope hypothesis, okay? And what I suggested is that these black holes have nothing at all to do with mass or with gravity. It's not a gravitational phenomenon. Okay, that's what I say. I say it's a magnetic phenomenon. It invokes the magnetic field of the galaxy. Okay, and so now we have this, this article, this headline that came out. It says the following. It says, twisting magnetic field observed around Milky Way's central black hole. And they go in here and they say, astronomers on Wednesday announced that they have detected a strong and organized magnetic field twisted in a spiral pattern around the Milky Way's supermassive black hole, revealing previously unknown qualities of the immensely powerful object lurking at the center of our galaxy. So these people think that it's all caused by mass, and that the mass somehow has all these magnetic fields around it, these strong magnetic fields around it. And so it says, this indicates that strong magnetic fields may be a feature common to black holes. Yeah, because black holes are nothing, as I just said a minute ago. In other words, a black hole has no singularity, right? It has no size, no volume, no length, no width, no height. Singularity has no size, no shape. And it crushes all matter out of existence. Therefore, it has no mass, because mass is a measure of the quantity of matter. There's no matter because it's been crushed out of existence, so there's no mass. So we have so far nothing. We have singularity is a volume-less, massless thingy, meaning it's empty space. It's nothing. And so, yeah, you cannot say that a black hole caused that pattern there. No, it's all magnetic fields. And so what are we talking about here? Why am I saying that it's a magnetic field, right? And by field, I don't mean the word field used in math, which is just a bunch of numbers. I'm saying a field is made of threads. Okay, those lines of force that Faraday talked about, those lines are not lines, because lines is not a word that belongs to physics. We don't have lines, especially one-dimensional lines in physics. So either you have a three-dimensional thread, like I propose, or you better find out what those lines are. Okay? And they never did. They just say we use them only to explain or to illustrate, but they don't really exist. Okay, so here's a ball in a magnetic field. Okay, what does a ball do when you put it in a charged ball, as they call it, right? A ball that's got a magnetic field around it, all these threads around it, really, right? But they call it a magnetic field, and they say this ball does the following. This is not mine, this comes from them, okay? This is what you do, what you find. And if you have a magnetic field, we'll call it a field, flowing downwards, whatever that is, right? A charged ball will move around in circles. Okay, this is well known, this is well settled, okay? There's nothing new here, okay? Okay, so how does the rope model treat this? Well, we say that all these so-called fields are made of threads, and here it is, okay? What you have is these threads coming down on and push up against the threads that are making the magnetic field of the ball, the so-called charged ball, okay? And so what you have is threads against threads. That's why the ball moves around. The threads are not really moving the ball itself. It's moving the threads, the charged part of the ball, which are all those threads that we cannot see or touch. But fields can touch fields. Okay, why? Because we're talking about countless threads. Okay, and the threads here, as you can visualize or can try to imagine, are coming sideways, pushing against the threads that are coming sideways around the little ball there. Okay, so that's our model for why a ball moves around in circles, because the ball is charged, meaning it's got all these threads flowing through its north pole, we'll call it, and down the sides and up its south pole. And the same thing happens with the fields that you see on the sides. Those come from whatever object is there. So these fields are flowing, okay, and they move this charged ball all around. It's field against field. In other words, threads against threads. Now we're talking about things, right? We're having threads pushing up against threads. Countless threads against countless threads. Okay, and that's where the ball just turns around. Okay, so let's look at a galactic field. This is what a galactic field more or less looks like, okay, under our model. And it extends way beyond the last stars, okay. What are those threads? Where do they come from? Well, they come from the atoms that form the stars that form the galaxy. Okay, so all these threads are thrown up, we'll call it through the North Pole, come down the sides of the galaxy and go up the, we'll call it the South Pole of the galaxy. Okay, that's more or less our model. Okay, okay, and so what do we do with this? Can we do anything with these fields, these magnetic fields? Well, here you have what they do to a charged ball, such as a star. Our sun has magnetic field around it, meaning it's got gazillions of threads coming out of its north pole, scanning down its sides and coming up its south pole. So it looks more or less like what you just saw a minute ago. And here we'll see it again. Okay, there you see the magnetic field. It looks more or less like a charged ball. Okay, well, here you see a star, and it's being moved around because what? A star is a charged object. Also, it's got a field, a magnetic field around it. And so we have the galactic magnetic field interacting with the star's magnetic field. That's what's happening. That's why a star moves around nothing, not because there's a mass in the center of that orbit, but because it's the galactic field, or in other words, the threads, right, that form the field, are pushing up against the star's magnetic field, the threads that form the magnetic field of the stars. Okay, so that's more or less the theory, okay, that we're saying. It's got nothing to do at all with mass or with gravity. It's a magnetic phenomenon completely. And here we have the jets. You know, they talk about these jets that come out of black holes, the center of black holes, and there's one in the center of every galaxy. So out of every galaxy, you have these jets popping out like a spring, right? And here you see it, okay? And you can see this is the jet from the black hole. But what is it? When you look at it, it's the magnetic field coming out of the center of the galaxy, meaning all the threads that are pushing from the center of the galaxy move around the galaxy, come up through the south pole of the galaxy, right? And back up through the north pole. And that's what these jets are. These centers of galaxies have all these so-called jets because they are magnetic fields, as the article said, right? Coming out of the center of all galaxies. You should have this in center of every galaxy. In fact, they say every galaxy has a black hole. Why? Because they see these jets. Why? Because those jets are threads, actual physical threads coming out of the center of the galaxy, moving around the galaxy, flowing around it, moving stars around, which are charged objects, right? And coming then from the south part of the galaxy and upwards again to the north. That's more or less what the theory is. That's why we don't need these black hole jets. We don't need gravity. We don't need mass to explain what we're seeing out there, the orbits of stars around nothing, or stars being stripped, flayed alive. They're stripped of their gases, their surface gases. All that can be done with magnetic threads, just pounding a star that is in the wrong, a beleaguered star that is in the wrong part of the galaxy. Sometimes it could be that two galaxies are close together, and you have the magnetic field of one galaxy interfacing with the magnetic field of another galaxy, and there's a little star there that is being pounded by threads from both galaxies. So that could also be the case for black holes. There's different scenarios, and they need to be explored, but under the magnetic field and not under the mass gravity scenarios. Okay, so where do we start with this history? Well, how do we end up with this mass, black hole, and all this nonsense? Okay, dark matter and dark energy and Big Bang and all this space-time. My God, they've created such nonsense. Well, here's our starting point, more or less. This is not really the starting point, but I guess it's one of the main milestones. And it was the peripatetic school created by Aristotle, known also as the Lyceum in Athens. And the reason it was called peripatetic is that good old Aristotle, he wasn't from Athens. He was not a citizen of Athens. He was from up north. He was from Philip of Macedon's reign, right, of his realm, I mean. And he came down and he put this school. And he became famous in part because also he was the tutor for Alexander the Great. And he comes down to Athens. He began to teach, but peripatetic means that you don't have really a place where to stay, that you would walk around and teach here and teach there and teach everywhere, right? And that's why it's called peripatetic. So what's the issue? Well, we're going to look at two of these guys. We're not going to look at all. One is that one there, Aristotle, the guy who's got his back turned towards you. And then the other one is the guy on the right. So let's look at both of them. These are the two fellows. That's Strato there, okay? And so these are the two fellows that we're interested in today, at least, somewhat. I mean, that's going to be our introduction. Okay, so what do we have? Well, we have Airy here, and what did he have to say about gravity? That's what we want to see, okay? And this is what he had. He had this geocentric model, right? He believed that the Earth was the center of the universe, I guess, of the solar system, or whatever was available to his eyes, right? So they had this geocentric model for the solar system. Objects immersed in a medium tend to fall at speeds proportional to their weight. This is a big criticism of Aristotle that everybody's had for hundreds of years now, that he's thought, right, because without doing an experiment, they say he just thought, he imagined that an elephant has to fall, faster to the ground than, I don't know, than a pebble, okay? And that is not the case. What is surprising is the elephant falls at the same acceleration, right, and fall at the same time at the ground as the pebble when they're thrown from above. So that's what people have a hard time understanding, that, that it's counterintuitive. One would think that the heavier object falls faster. That is not the case. Aristotle screwed bigly on this one because everybody just threw this at him ever since they read Aristotle, okay? As all bodies move toward their natural place, water is concentric shell around the Earth. Because Earth is heavier, it sinks in water. So Earth sinks in water. So we have this, I guess, ball of water, and the Earth sank in it somehow. I guess, I don't know how you visualize this. Maybe you thought water was like an ocean, and Earth was like a buoy just sinking in it. I don't know. And then you have air is a concentric shell surrounding that of water. Bubbles rise in water, okay? So you had some things that went against gravity, the bubbles, right? Fire is higher than air, but below the innermost celestial sphere. Yeah, they figured out that fire can go upwards against gravity, like, when burning a tree or whatever. And there is no effect or motion without a cause. The problem there is that we don't have a good definition of what cause is. Here is the definition we see today. Let me get this one out. This is the definition we have. It says causality, an influence by which one event, process, state, or object, a cause, right, contributes to the production of another event, process, state, or object, an effect, where the cause is partly responsible for the effect and the effect is partly dependent on the cause. No, we got to get rid of all that. That's not what causality is. Causality is objects, only objects and solely objects. We don't have any concepts such as what? Event, process, state. None of that has any bearing on causality. In physics, an object causes something else, okay? And so only object can cause, can cause causes in physics. Okay, you cannot have a cause by saying, a process caused it. No, you can't use the word process in physics to say the process, this concept, dynamic concept, caused something to happen. You have to say it was the table that broke the window, for example, right? You can say that, but you cannot say the process broke the window, okay? Or the event or whatever. No, the event, what you're trying to explain. And so causes only have objects as mediators. And physicists, mathematical physicists, never understood that. They never realized that you cannot use, especially mathematical concepts, as mediators for causes, for explanations, for mechanisms. And that's why we don't have any today. They don't know what, they don't understand. They cannot explain what gravity is, what the mechanism of gravity is. What, John Bias? He has no clue. He says that's not part of science. Why? Because he cannot explain anything. Why can he not explain anything? Because he never used objects in his life. He's using numbers, he's using abstract mathematical concepts. He uses them in lieu of objects. That's what the problem is. Okay, here we have good old Strato. What did he have to say? What did he disagree with this other fellow, with Aristotle? It turns out all these guys were the people who succeeded Aristotle as head of the Lyceum. Okay, so it says rejected Aristotle's natural places, proposing mechanical view. Objects do not gain weight as they fall. Greater impact is due to an increase in speed. Falling bodies accelerate. I guess he realized that they go faster, faster, and faster. We speak of more or less time, but not a quicker or slower time. That was neat. Motion can be quicker or slower, but the quantity, time, in which the action is not quicker and slower. That's good. Yeah, time doesn't go faster or slower like in relativity. Time always proceeds at its own rate. Okay, time doesn't change. Okay, the Earth goes around the sun. It takes so many hours, so many days, so many seconds in the year, but always at the same pace. Okay, and it doesn't go slower or faster. But your clock might go slower or faster if you get farther away from the Earth. That's got nothing to do with the second, which was originally defined as a portion of the year, which is one revolution of the Earth around the sun. And then he suggested that all matter consisted of tiny particles. I guess he was like Democritus. He believed in it's only particles, empty space. But then he rejected Democritus' theory of empty space. He says there is no such thing as empty space, but he qualified that. Void exists only in the empty spaces between imperfectly fitting particles. So there is space, whatever that is, right? He never, I guess, defined what void is, what space is, but he says there is a little hole there and we're just going to ignore it, but other than that, it's just a bunch of particles out there. And space is always filled with some kind of matter, and theory permits phenomena such as compression. In other words, by allowing a little bit of space, a little bit of void between the particles, well, he enabled, compression. Yeah, but then there either is a void between particles or there ain't. Can't be both ways. He says there is, but it's so tiny that it's negligible, and we're only going to use it to explain compression. Other than that, we're not going to use space at all. There is no such thing as space. It's all particles. And that was the ether, essentially. That's what they always thought about as the ether. Some see the ether as a bunch of particles which are standing still, a sandbox, and the Earth moves through this sandbox. And other people think that ether is this dynamic balls that move, I don't know in what medium. What is it, space? You would have to tell us what space is before you do that, but they think that these particles can move, they can vibrate, they can oscillate and create waves and whatever. And so, yeah, it's a bunch of particles. And so we don't care if it's a sandbox or this flowing ocean. You have to tell us what it is. You have to illustrate if you're going to use ether as an object. Either you use the little balls or you use the ether, the whole ocean. And if you use the whole ocean, you got to use it completely. You can't use a piece of the ocean and say, well, I'm going to look at this little water, how it vibrates here, but I'm going to call this the ether. You can't do that. Ether is the whole universe. Okay? You can't say the universe moved. Okay? So either you use the whole universe or you use a little piece and you give it a different name. The ether is the whole universe. Okay? All the particles. And obviously, all particles is not a thing. It's a concept, dynamic concept. Okay, here we have Aristarchus, and he said the following. He had these ideas. He believed in the heliocentric model of the solar system, or universe, right? And stars are bodies like the sun. Stars are very far from Earth, and stars and sun are motionless. Okay, so he believed the sun did not move. It was the Earth that moved around the sun. and therefore the stars out there in the background, they were stapled to some kind of firmament, and so they didn't move either. And so, they had these ideas, and they tried to make them, reconcile them with gravity. That, they realized that all these, like the sun and so on, they had some influence over the earth. And they called that, they had this notion of gravity, but they didn't really know how that worked. In fact, they still don't to this day. But they realized they knew what gravity is. They knew that things fell to the ground. They couldn't explain some of those. They said, well, some of the heavy ones fall. Others, like the feather, that floats or takes longer. If we had a balloon, or they would have had one in those days, it would have gone upwards, So the question is, what is this thingy called gravity? They had just the rudimentary notions of what gravity is. Okay, then we get to the days of the Romans. We're going to just skip here a little bit. And we have this of Vitruvius. And Vitruvius, he wrote a book, De Architectura. And he was an architect and engineer. And he says, gravity is not dependent on a substance weight. Okay? So he had this notion already in those days as an engineer, right? It is dependent on its specific gravity. That was what he came, that's what the conclusion to which he came, right? Then we have this other fellow, he's a little more known, his name is Lucretius, and he wrote this book, De Rerum Natura, and it's really a poem, right? He wrote in form of poetry, and he says, more massive bodies fall faster in a medium because the latter resists less. He realized that, things float in water, they don't fall like a stone falls on earth. In water, they fall slower, and some even float. And so, but he said the following, he said a very important point there. In a vacuum, all fall with equal speed. That's very interesting that he said that they all fall with equal speed, because that kind of preempted good old Galileo, at least 1,500 years earlier, right? And here's what Lucretius said in more detail. Okay, it's important to see him. It says, bodies in space cannot move spontaneously from down to up. Okay, so he realized something very important. They don't rise except maybe birds. And this is not contradicted by the blaze of the burning objects. In other words, the blaze can go upwards, okay, the flame. Also, golden cereals and trees seem to be projected towards the sky. In other words, all these plants, they grow upwards against gravity, right? But heavy bodies cannot avoid falling down. Wooden planks are projected up from water but fall down in a vacuum. Okay, so you can have the plank float, right? Boats and so on, but you put them in a vacuum and somehow they fall. So he already realized this, and he suggested they all fall at the same rate, which again, I guess he preempted good old Galileo there. While atoms are driven up by their weight in straight vertical falls through the vacuum, they happen to be casually deflected from their trajectory. What is he saying here? Well, he had a problem because he said the atom was the smallest bit of matter, and he had a problem with that because he talked about collisions and other things that happen out there in this invisible world, and he had a problem with them falling completely straight down without hitting anything. So he says sometimes they are deflected from their trajectory. Okay, he was suggesting, because what he was gearing towards, he was trying to get to free will. He was trying to say that not everything is deterministic, but there's free will, because you can, avoid a tree. Like instead of crashing, you can go around it. And he was suggesting that the particles had this ability sometimes to be deflected, swerve from their rectilinear trajectory. In absence of this swerve, they should fall regularly and eternally like raindrops. No atomic collision, and consequently no process of generation of the world should have been possible. And he's talking again about free will. That's what he wanted to get to, but he never clarified really what he was talking about, because he had a little contradiction. Maybe he realized that in his theory of physics with respect to the living world, the world of the living. Okay, here we have two fellows, and it's important to note them because both Pliny the Elder first, and I don't know if Claudius knew about him or what his studies or what his conclusions were, but Claudius came to the same conclusion, that the moon gravitationally affects the earth tides. They realize this. And you can see there in the pictures why that's the case. Okay, as the moon is on one side of the planet as our planet spins, well, the moon always pulls on the tides, on the water. And that's why sometimes the tides are bigger closer to the moon. Okay, and and Newton is going to rediscover this many years later, but this is already written in the books by Pliny and Ptolemy. Okay, here's another fellow who discovered something that we always ascribe or attribute to someone else, and that's this fellow here, John Philoponus. And he said, if you let fall from the same height two weights, one many times heavier than the other, you will see that the ratio of the times required for the motion does not depend solely on the weights, but that the difference in time is very small. In other words, he was saying they fall at the same time. He could not precisely figure out if there's a small difference, but he says, but it's very small, if anything. And so he had these notions. Substance refers to material objects. Okay, he had that more or less on the spot, but he never said what substance or material objects are. Okay, substances require some determinate quantity for their being. He was introducing math. He was saying, look, we're going to look at quantity, such as weight or mass. He didn't discover the notion of mass, but he had the notion of weight. He rejected immaterial things, okay? And he says space is an immaterial three-dimensional medium in which objects are located, okay? So he's saying space is not a thing, which is correct. It's immaterial, but he says it's a three-dimensional medium. So he's got a contradiction, because three-dimensional is something you ascribe or attribute to objects, the things, the bodies. The hurled body acquires motive power, force movement from the agent producing the initial motion. This power secures the continuation of motion. Impetus comes to an end. In other words, he's saying this thing that you push, that's what gives it the force, right, that you need. And he says there, this is a quote from his book, if an arrow or a stone is thrown into empty space, nothing is necessary for this except the thrower. In other words, it will continue going and going and gone, right? You can throw it forever. He would say empty space, nothing stops it. In other words, that was his notion, right? But it done a couple of centuries later, we have this fellow. His name is John Bourdon, and he's a Frenchman, and he really gave the word impetus to the theory, even though the theory came from Philoponus. But he says the following. He says he took the initial stage of Philoponus and the intermediate stage. There you see the two of them. But he added the last stage. He says gravity alone draws projectile downwards vertically as all impetus is spent. So what is he saying? He's saying that unlike Philoponus, who says, if you throw a stone, it'll go on forever in empty space, right? And unless something stops it, this fellow says it's going to be gravity that finally pulls it down, whatever gravity is, okay? So you can see these notions started appearing. People started saying, well, why does a stone fall? Why doesn't it continue going forever? And even Newton realized that, He analyzed that in more detail, okay? Okay, so here's two fellows who also preceded Galileo. I like to always show this because people say, oh, Galileo, he took the two stones to the Tower of Pisa. And maybe just two pizzas to the Tower of Stone, I don't know, and just threw them from up there. And here it is, and these fellows, 1544. Look at the date Galileo was born. He was born in 1564, 20 years later. These two fellows on the left, they already talked about two stones being thrown from a high place and hitting the ground at the same time. So Galileo did not invent this. He did not discover this. He just learned it in school or wherever, certainly from Moletti, who was his predecessor at the University of Padua, or either Padua or Pisa. I can't remember now which of the two universities. But these two fellows preceded him by 20 years. They already wrote about two stones hitting the floor at the same time, or two wooden boards. Then we have this fellow, 1551, 7 years later, he wrote a book about it as well. And finally, this fellow, for sure, Simon Stebbin, we can find his book today, The Principles of the Art of Weighing. And he went to the Delft Tower in Holland there, and he did the experiment. He took two stones together with another fellow, and they both hit the boards at the bottom at the same time. And they did the experiment many times until they were convinced that the two stones always fall at the same time, even though they had different weights, different sizes, different whatever. Okay, so Galileo was preempted by all these people. They already beat him to it. Okay, so here's good old Galileo. What did he do? Well, he says spaces traversed in natural motion are in the square proportion of the times. So he kind of also preempted Newton, who is credited with that. He's saying square proportion of the times, whereas Newton said square proportion of the distances. But here you have his book, Two New Sciences, and he says the difference in speed of different masses is due to air resistance. Otherwise, they fall completely at the same time in a vacuum. So he just repeated what people taught him. He did not come up with this on his own. I doubt very much he went to the tower and threw two stones to verify that. He probably, what is believed that he did, that he rolled balls of different weights, etc., down inclined planes. Okay, and then he kind of measured them, I guess, with a water clock. Okay. Here's a contemporary of his. His name is Descartes. Okay, good old Rene. What did he do? Well, first of all, he came up with this notion that if you have a sling shot and you twirl it around, the ball does not go along the tangent when it's released. It goes in a straight line from the hand to where it is at that point. So he kind of highlighted this. He's saying, the gravity kind of works like that. It works towards the center of the earth. And so he was inferring or insinuating that this is more or less one of the characteristics of gravity. So he was just analyzing that. He's saying, look, it doesn't go along the tangent. Okay, there you see the tangent red line. Okay, so what did he come up with? Good old Descartes. He came up with the vortex theory. What is it? A large circling band of material particles. So he had this circling band of material particles. They swirled around like a tornado, essentially. Okay, that's what you got to think of the vortex as. And he says planetary orbits are situated in circling bands. So you have this poor old planet which is caught up with all this dust around it, which is swirling like a vortex. Okay, and he didn't believe that there's anything such as empty space. He thought all of the universe was a sandbox, but it was a moving sandbox where you have all these vortices all around. Okay, and he says the plenum consists of a network or a series of separate interlocking vortices. Okay, so they're all kind of connected to each other, or they're all influencing each other. And the matter within the vortex has formed itself into a set of stratified bands, each lodging a planet. And so he's got the primary matter, which is the fine stuff, you could say the subatomic or atomic stuff, that I don't know how you really imagine this, but it was the small stuff. Indefinitely small globules that fill space entirely and form the background of ordinary matter, which means he was talking about the ether. That's what the ether is. Okay, so he had this ether. He was an etherist, by the way, Descartes. So he thought of this ether as a bunch of particles that just fills the entire universe. Okay, and some places, close to the sun, I guess, they had all these swirls, all these vortices, and those swirls what kept the planets in their orbits. Each planet was stuck in a swirl, in a vortex, and it had no choice but to go around in circles around the sun. Yeah, and of course he believed in the the heliocentric model, right? Secondary matter, what is that? Well, minute material particles, the one we just covered, the primary matter, that form the vortex bands consist of primary matter left over from the impact and fracture of the larger elements. So the secondary matter are pieces of dust that are out there floating around. And then the tertiary matter are the big guys, comprises the large macroscopic material element. This three-part division of matter, along with the three laws of nature, are responsible for all cosmological phenomena. Okay? So he was saying that all the orbits from the planets, what Kepler had more or less discovered, what the ratios of the orbits were to their radius, all this kind of stuff that he came up with. Rene was trying to explain that. He's saying, look, it's all these vortices we have out there, and the whole universe is filled with all this dust, all these particles. There's no empty space in Rene Descartes' world, in his vision. But the problem there is what separates one particle from another. If not empty space, what identifies each particle? Because if each particle is surrounded by a surface, we'll make them cubic to make it easy on him, right? Even one cube from another cube, what separates them? Why aren't they merged and form a single block? The block universe, just single block made of a single piece. So he's got a contradiction in his assumption, already, his hypothesis. And so, he came up with this notion of gravity, and this is what he believed in. He says, cosmic gravity, all these minute particles that surround the Earth account for terrestrial gravity. And a planet comes to rest in a vortex band when its radially directed outward tendency to flee the center of rotation, right? The centrifugal force is balanced by an equal tendency in the minute elements that comprise the vortex ring. So all these particles are preventing the Earth from flying outwards. Okay, so you had all these vortices swirling around the Earth, the ball, known as the Earth, and at the same time, the Earth was flying around the sun because it was caught in a bigger vortex. Okay, so we have the little vortices and those big vortices. It's the little vortices that keep the Earth within its big vortex, because it doesn't allow the Earth to move inwards or farther out from the sun. And then within the bigger vortex, the vortex swirls the Earth around the sun. Okay, so we have all these vortices. That's one vortex inside another vortex. If the planet has either a greater or lesser centrifugal tendency than the small elements in a particular vortex, then it will respectively either ascend to the next highest vortex or be pushed down to the next lower vortex. But I guess he didn't believe that happened. It says if. It's an if question. But he essentially believed that the small particles kept the Earth within the big vortex, and the big vortex is the one that swirled it around the sun. That was his notion of gravity. Just a bunch of vortices in contact with the Earth, preventing it from going outwards or coming inwards. Space-time is more or less like that. You have bent space-time, warped space-time, right? And the Earth cannot push outwards. One of the questions is, why does it roll inwards, right? Why does it come towards the sun if it's a depression? Why doesn't it fall down the depression? Okay, what keeps it in this centrifugal, right, motion? Why is it pushing against the depression? I mean, it should roll downwards, right? That's the way they always illustrate it when they put the black hole. They say you have a black hole, it's deep, and anything that goes in there falls all the way to the center of the black hole. Okay, we all understand that. I played marbles. You got a hole, you throw the marble, and the ball falls inside the ball falls inside. The marble falls inside the hole. And why doesn't the Earth fall to the center of the sun? What keeps it pushing against the depression? That's the question. Okay, food for thought. Okay, and then we come to the days of Newton, a little later, the same century. But Newton was born when Galileo died. And so he's got this ether. He believed in the ether, and so he's going to have this ether / gravitation hypothesis. Ether is a medium susceptible to vibrations. That was his notion, right? So he thought of the ether, again, it's a bunch of particles. He believed in the particle theory, and he thought it's a medium, meaning all these particles make some kind of medium, which ain't true, because a medium, a table is not all the atoms that make a table. Table is that thing I'm pointed to. So either you talk about the ether, which is the whole medium, or you talk about the particles that make up the medium, the ether. So you can't talk about both and mix them and talk about the ether and say the ether does this and that. No, you got to talk about the particles doing this and that. Can't say the ether is the entire universe of particles. The gravitating attraction of the Earth is caused by the continual condensation of some other such like ethereal spirits. Okay, he's got this ethereal spirit, right? That's going to do this work that he can't identify. Something very thinly and subtly diffused through it, perhaps of an unctuous or gummy, tenacious and springy nature. That's how he imagined the ether. Okay, such an ethereal spirit may condense so much as to cause what? It from above to descend with great celerity for a supply. So the ether is going to push us downwards, right? In this descent, it may bear down with it the bodies it pervades. It's going to push on us. It's a push mechanism that he's thinking about. The ether is pushing on us with force proportional to the superficies of all their parts it acts upon. And as the earth, so perhaps may the sun imbibe the spirit copiously to conserve his shining and keep the planets from receding further from him. In other words, he was saying, again, more or less like Descartes, that you have all this ether, and somehow the ether pushing down on us on Earth, but somehow the sun, is pushing on us and pulling on us and preventing us from moving farther away or even closer to the sun. So again, we're in the sandbox, because the only way you can explain that is with a sandbox there. Even Descartes, vortices would have, you would think the Earth would be, moved around a lot, because you have all these vortices which should not be in any with any uniformity. They should just bang you from every side at any point, just swirling around, and so we should be rattled. And that's not the case. The Earth doesn't get you rattled. It goes smoothly around the sun. And so Newton also had this problem. Are you going to have this sandbox, or are you going to have an ocean? If we're an ocean, you can talk about swirls and a lot of other stuff. But if you have a sandbox, you got a different problem. Try to put a ball in a sandbox, see if it moves around. You're going to have a hard time. Okay, so Newton comes up with this notion, which we have today, unfortunately, known as, the dichotomy between mass and weight. Okay, he created this dichotomy. And in his Principia, he says the following: the quantity matter is the measure of the same arising from its density and bulk conjunctly. It is this quantity that I mean hereafter everywhere under the name of body or mass. So Newton is going to replace the word body with the word mass, or make them equal. He's going to make them synonyms. He's going to talk about mass, and he's going to move the mass because he's moving a body. Okay, and this horrendous, match, this synonym. These synonyms have lasted even to this day. Everybody in mathematical physics treats the word mass as a body, and it came from him, from Newton. And the same is known by the weight of each body. So he's saying that mass and weight are the same, for it is proportional to the weight. So he's saying mass and weight are the same thing, because mass is proportional to the weight, so you can almost use the word weight to qualify mass. Okay, I don't know if he understood that if you took the mass to the moon, it had a different weight. Maybe he didn't understand completely whether weight was a gravitational phenomenon. And he says, all matter attracts all other matter with what? With a force proportional to the product of their masses and inversely proportional to the what? Square of the distance between them. Whereas Galileo has said square of the times. Okay, but again, people already had this notion out there. In fact, one of the first persons to have it is good old Robert Hooke, which Newton trashed as much as he could. The Principia deals primarily with what? Massive bodies in motion. So he's going to talk about not objects, but he's going to really talk about math. He's going to mathematize. He's going to quantify motion. That's what he's going to do. He's going to use the word mass. He's going to talk about kilograms, and he's going to move the kilograms. Offers criteria to decide by observation which laws of force are operating in phenomena that may be observed. Explores difficult, in other words, mathematical quantitative problems, right, of motion perturbed by multiple attractive forces. So what Newton does really is he's going to be talking about math. He's not going to be talking about physics. He's going to call a body a mass and a mass a body. So he says they're synonyms, and so is weight, and they're all synonyms. And he's going to talk about mass. He says there's so many kilograms that are moving, and he's saying, I'm saying that a body is moving. Yeah, you know what I mean? And that's lasted until today. And that was a big crime that he committed, because they haven't come out of that. Okay, one of the right-hand men during a period of time was Nicholas Fatio. Okay, and Fatio said the following: And he created the push or shadow theory of gravitation. Okay, again, particle man. All these people were particle men. And he says the force of gravity is the result of tiny particles, corpuscles, moving at high speeds in all directions through the universe. The intensity of the flux of particles is assumed to be the same in all directions. So an isolated object A is struck equally from all sides, resulting in only an inward directed pressure that no net directional force. But no net directional force. And there you see the example. You have all these arrows pointing towards the object if nothing gets in their way. But what happens if you put two objects? Well, with a second object B present, however, a fraction of the particles that would otherwise have struck A from the direction of B is intercepted. So B works as a shield. The same thing happens from the other side, for A. And so A and B are shadowing each other, and the two bodies are pushed towards each other because they're both blocking particles that would otherwise be hitting the other object away from it. So in other words, they're being pushed from the outside and blocking the particles that would otherwise hit the second object. Okay, and that's why there's attraction between bodies. It says diminished push from the direction of the other bodies. Okay, so you can see there A and B, they're attracted to each other because the particles between A and B essentially are diminished. That's it. That's the push mechanism, or fascio, whatever his name was, theory of gravity, now known as the Lesage theory of gravity. Absolute poppycock nonsense. You can't explain gravity with this nonsense. That's why nobody adopted it. Very few people still talk about push gravity out there, but yeah, they need to go to psychologists or psychiatrists to the shrink, not to physics class. Okay, here you have two fellows who criticized, one guy criticized him, Newton, which is Leibniz. They always had a little fight there, first of the calculus, and then Gottfried also criticized Newton's theory of gravity because he says he invokes action at a distance. In other words, Newton had no mechanism of gravity. Okay, it's invisible, intangible, and not mechanical. And so he criticized Newton, and Newton says, look, I don't purport to know what the cause of gravity is, which is what physics is about. All that Newton did was describe and say, look, this is the way acceleration of gravity works. This is, if we measure it, this is what you'll get. But he said absolutely nothing about the mechanism. And Voltaire, on the other hand, he came a little later than Newton, but he made Newton famous. And he said the following. He went to England, came back to France, and wrote this book in which he tried to convince people that Newton was a genius. And that's how Newton became famous, really in France and then later on in the world. It says Newton's notion that gravity is proportional to the masses of bodies and inversely proportional to the square of their spatial separation explains. No, he meant describes, not explains, the fall of bodies on Earth, the tides, and various astronomical phenomena. Descartes' vortex theory fails to do this. Okay, he's right that Descartes failed, but Newton failed as well. In other words, Newton could not explain with his particles what the mechanism was. And that's more or less what Leibniz was saying. He was saying, look, Newton cannot explain gravity. He cannot explain the cause of gravity. He's using action at a distance, meaning black magic, right? That's what it's called, witchcraft, okay? So he had no mechanism for why gravity acts the way it does. Here we have this is now in the 18th century, pretty much. And in fact, I think it happened in the 1790s, so it's completely in the 18th century. And that's, I think, the last little thing that was contributed to gravity. You have Cavendish torsion balance, and he was able to calculate the gravitational constant G, which was necessary to complete Newton's equation. Okay, so we have that gravitational constant G. Unfortunately, what these people do is they put 10 to the minus 11 meter cube over kilogram second square. They have no idea what all that unit means, and they have 10 to the 11 minus 11. That's why they never will figure it out. All they had to do all these years is multiply that 10 to the minus 11 by the mass of the atom, of the hydrogen atom, and they would have figured it out. Okay, and they did, so we do it here. Okay, there you have it. If you multiply that times, what is it, 10 to the 16th, I think it was, 9e16. Well, you get this number there that gives you the mass of the atom and the velocity of light squared. Okay, so once you have that, you have the mass of the hydrogen atom, the velocity of light squared. Now you remove those from the gravitational constant G, and you're only left with that 0.44 meters per kilogram square, which we define in the book. I'm not going to go into details here, but we've factored out these two important variables or constants, which are the mass of the hydrogen atom and the velocity of light squared. Okay, so this is what they should have done, and to this day they haven't figured this out yet. Someday they'll read my book and they'll figure it out. Okay, what the gravitational constant G is made out of. Okay, what its components are. Okay, and the final fellow who contributed something to gravity is this fellow. His name is Albert Einstein, and he came with the most ridiculous physical interpretation he could come up with, which is warp time. He's saying that warp time prevents the Earth from flying out. Again, we don't know why the Earth fell to the center there, especially if that canvas is warped by the sun. The Earth should be falling towards the sun. They never explain why it doesn't fall towards the sun, why it keeps rolling around the edge of time there, of warp time. And there you have his field equation, which is really a matrix. Okay, it's really a set of 16 equations, right, that you can use to calculate things. And it doesn't tell us, again, it's just a description. It's not a theory. The theory is the warp time, the mechanism. That's the theory. The mathematical garbage that he's got at the bottom, that's only a description. We don't care about that in physics. Physics, we care about the mechanism. Why doesn't the Earth fly out of the solar system? They have never explained that. In fact, they cannot explain, why little spoon, right? Why it falls to the ground. Something as simple as that, they cannot explain it. Okay, so did Einstein believe in his theory? Well, the answer is no. Okay, here he is. This is the last few days of his life at Princeton. And these are notes and letters that he wrote to friends. He said, I'm generally regarded as a sort of petrified object, rendered blind and deaf by the years. Why? Because they put him in a corner and they forgot all about him. All they did was use his name, saying, oh, the great Einstein, he did this, he did that. And today even you have to write, everything you write today has to mention Einstein. But nobody realized that Einstein was put in a corner with a dunce cap on his head, and everybody just laughed at him. Okay, and then why in great measure? Because he did not believe in quantum mechanics. That was his main crime. But he also lost faith in his own theory. And here you'll see it. I have become an obstinate heretic in the eyes of my colleagues. And then he says, all these 50 years of conscious brooding have brought me no nearer to the answer to the question, what are light quanta? Nowadays, every Tom, Dick, and Harry thinks he knows it, but he is mistaken. I consider it quite possible, listen to this, that physics cannot be based on the field concept. In other words, on continuous structures. In that case, nothing remains of my entire castle in the air, gravitation theory included, and all of the rest of modern physics. Okay, so Einstein became an atheist in general relativity and quantum mechanics towards the end of his life. He didn't believe in any of that. Okay, he lost faith. When the Pope loses faith in God, you got a little bit of a problem. Okay, so was this so hard? I mean, why did we take 10,000 years not figure out why this spoon falls downwards to the floor, never to the ceiling? That's all we had to explain all these years. What was the problem? Well, the problem was that we never identified, or the mathematical physicists or the people who did research, whatever, they never identified the invisible, intangible mediators that we have here. You cannot see it, you cannot touch it, no experiment you can run, you cannot go to the lab, to the field and say, I'm going to run an experiment. There's no way you can detect. That which is invisible and intangible, you cannot use your hands or your eyes. Period. We're done. The way it works, you stay in your office, you do some armchair, what's called armchair physics. You put your feet on top of a desk, okay? Beer on your right hand, beautiful girl on your left hand for inspiration. And you start trying to visualize what could be causing gravity. What mechanism does Mother Nature use? what is there in that invisible, intangible world of Father Universe and Mother Nature, God, the devil, whoever you believe in, that makes this phenomenon, that causes this phenomenon. And here you have a clue. Good old Richard Miller, he's a professor at the UC Berkeley, and he says the following. He says, if you have the earth, there's a big mass here, and you have you with your little mass here. Okay, there he drew a picture on the blackboard there. You have your little you sitting on this big mass called the earth, right? It says every atom on earth is pulling on every atom of you. You're also pulling on it. Oh, how do you pull unless you have a mediator between the atom of the earth and the atom of you? Okay, in order to pull, you need an elongated object. Invisible, intangible, elongated object. And he says the amazing thing about gravity is that it goes right through things. Yeah, if it's an invisible, intangible, elongated object, it goes right through you, goes right through other atoms, and continues to another atom. It's known as the rope hypothesis. Okay, and here you have our version of that, of going through and also pulling, because you can only pull with elongated objects. Here you have one. You have a spoon falling to the floor, and every atom of the spoon is bound to every atom on Earth. And watch what happens to every rope that connects every atom from one atom on the spoon to every atom on Earth, and one atom in the Earth to every atom on the spoon. Well, what they do is they fan out. As they fall, they get closer to the center of the Earth, the ropes fan out. That's the cause of gravity. Now we have a physical thing that we can all imagine, we can all visualize. Do you believe it? Well, we don't care. Belief is part of religion. Okay, we just explain a mechanism so that you can visualize it, you can understand it, and you can take it home with you and munch it and chew it and do whatever you have to. And if you believe it or not, it's your personal business. And here we have a astronaut falling to Earth. Okay, same thing. You can see as he approaches the Earth, the ropes fan out. Okay, very simple mechanism. Baby stuff. A 10-year-old can understand this, no problem. As he falls, every atom in his body is bound to every atom on Earth. That means one atom in his body is bound to every single atom on Earth. That means how many gazillions of atoms does he have in his body? How many gazillion, trillion, billions of ropes are there connecting him to every atom on Earth? You can imagine that, okay? Or maybe you cannot. It's unimaginable. We don't care how many. It's not a question of numbers. It's a question that the ropes superimpose. They can be on the same axis, so there's no problem there. And as he falls, the ropes fan out. They come out of the axis and act independently, or what we call effective ropes. Okay, each rope operates or functions independently as it separates from the axis. And at a great distance, in the great distance, far away from the Earth, the astronaut is like a little dot at infinity, we'll call it, right? And all the ropes form essentially a single coaxium.